Okay. So just remember for this one, if you're given a function, you're looking for the things that you learned before about domain, right? If you're dividing by 0, then that's going to cause a problem in the domain. If you're taking the square root of a negative number, that's going to cause a problem. If you're working with like a logarithm and the number is 0 or below on the inside, then that'll make a problem. Or like some of the trig functions. Hopefully you got a chance to look at those when you were being taught about tangent, secant, cosecant, and cotangent. Those ones have some dividing by 0 situations in them too. We'll talk about that as we go. All right, so let's look at the next one. So we want to know what's going on with this one. And remember what I said. We're looking to find some dividing by 0 issues, some square root of negative number issues, and some logarithms with weird stuff inside of them. So the question I have for you here is, does this have any of those issues in them? Is there any dividing by 0 errors? Is there any square root of a negative number errors? Is there any logarithms in here? Are any of those things present in this function? No. So do we even need to look at this? Like, because, okay, absolute value I know is always continuous. It just makes a V shape, right? Sine always looks like this, but it's always connected and always continuous from negative infinity to positive infinity. All of our normal functions are good. So when the answer to this is, hey, it's continuous everywhere. No matter what you try and plug in, there's no problem. And so our answer would end up being just straight up from negative infinity, positive infinity. So the thing about it is, a lot of these problems where they're asking you about where is it continuous, you're not going to sit there and like solve for what is. Your goal is to look for what is not. And so basically the best thing that you could possibly do is look for situations like this. If you don't have a variable in a denominator, if you don't have a square root, if you don't have a logarithm, and you don't have tangent, secant, cosecant, or cotangent, those are the only possible situations where you're going to have a continuity break with like a function like they wrote here. So if you don't have any of those things, then I highly recommend you just have that list in your notes just to pay attention. If you don't see any of those, then there ain't no problem anyway. And so just you don't even have to think about it. You could look at that one and go, oh, it's fine. Negative infinity to positive infinity. So don't feel like you have to sit there and figure out every single one. The only ones that you're going to actually have to identify or like work with are these. And if you're not working with any of these, and I'm going to say about 50% of the time you're not, like a problem like this, they would put that on there and make it all complicated looking, and then you'd go, oh God, what do I do? And it's easy because you just say, hey, there's no holes or anything or asymptotes. So it's all real numbers, negative infinity to positive infinity. That's all. But now here, cosecant. This is one of those ones where there's a problem. And the reason that there's a problem is cosecant is 1 over sine of x, right? So we have to look at the function in terms of sine so that we can figure out where the zeros in the denominator are, right? If we go through and we draw our unit circle, and we're looking, it's saying using pi as needed. This is a hint. We're always using radians for this. And they're going to ask you to, because remember that these functions just keep going around and around and around and around. It doesn't just stop after one revolution. So we're going to talk about what to do with this in a second. But like, you're going to go through and you're going to say, all right, well, in order for me to figure out what I have to kick out, I got to figure out where this is 0. Right? So we're going to figure out where this is 0. Well, where is sine 0? Where is the y value 0? Right? Here's where the y value is 0. So like 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So and so on, right? So the thing of it is, we're saying, all right, well, here's the way that I was taught to write it down. You'll only have to write down the expression. But this is when I was a kid, we would say let n be an integer then right 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, or the negative ones too, and pi, right? And then so now we have to look, because that's where sine is 0, but on the inside it's an 11 here. So we're going to do welcome back. So we know that the n pi, that's all the solutions that make sine 0 that we're trying to kick out. And we just need to say, okay, well, we want 11x to be this, so let's figure out the x value, and then we can just divide and solve for x. Trying to divide the wrong thing here. Divide by 11, right? And so this right here is what they're looking for, because they're saying type an exact answer using pi as needed, and they're saying type an expression using n, where n is an integer. And so this right here contains all the answers for what numbers cause sine to be 0 in this situation, so we can find the discontinuities. All right, so your final answer here, because it's saying everywhere except for, and then you'd say n pi over 11. All right, so don't think about these too hard. They're pretty easy to do if you write it out and you write out the unit circle and all that. It makes it a lot easier to look at. Okay? Okay. Same thing here. Now, the only problem that we're working with is we have two different caution signs, right? Tangents here, and we've got a variable in the denominator, so we are just going to have to do both. So let's do the variable in the denominator first. X squared plus 3 equals 0, and then we're going to figure out what values of x make this happen. Subtract 3. And then we're going to square root both sides. So we're going to have plus or minus. And I take the square root of a negative number. Am I allowed to do that? Not if we're working in the real numbers, right? So here, because no real number is going to give us 0 in the denominator for x squared plus 3, because you can't take the square root of a negative number. This is free to go. We don't care about this anymore. Now we just care about the tangent, right? And we need to know, where is tangent of x undefined? And if we break down tangent, remember tangent is sine divided by cosine, right? So we're looking at this and we're saying, well, where's cosine 0? Because we can't have a 0 in the denominator. And cosine is 0 at pi over 2, 3 pi over 2, 5, 7, 9 pi over 2, all those pi over 2 ones. So that's what we got. X cannot equal, and again, we're saying n pi over 2, right? Because 1 pi over 2, 2 pi over 2, 3 pi over 2, 4, 5, 6, 7 pi over 2, 8 pi over 2, 9 pi over 2, etc. And then 2 pi over 2 is this one. So we have to do this slightly differently. Couple ways to do this. Yeah, actually, let me show you. So n is an integer, and if we want only the odd numbers, right, because the even numbers are going to simplify and get you these, which we don't want. And you can always work with call an odd number this, 2n plus 1. Whoa, what's going on here? So look, if we use 2n plus 1, if we have n is 0, then we get 1. If we have n is 1, then we get 3 in here, right? 2 will give us 5, 3 will give us 7, 4 will give us 9. And so we don't have to like, so if you're ever looking, hey, I only want odd numbers, 2n plus 1 is always your best friend. Just like 2n would always be an even number, 2n plus 1 will always be an odd number. For n is an integer. And that's all. So to recap a little bit, there were two different possibilities for discontinuities. There was a variable in the denominator, and there was a tangent function. Each of these produces discontinuities. The variable in the denominator, we checked it and found that there's no value of x that makes the denominator 0, so we're good. We can ignore it. We come back for the tangent of x, and we say, all right, well, tangent is undefined where cosine is 0. And that's the pi over 2 parts, the pi over 2, the 3 pi over 2, the 5 pi over 2, the 7 pi over 2. And so we say, hey, we write it like this. Odd pi over 2. And that's all. So again, same thing here. We've got a square root, right? Square roots have to be positive, right? So all we're going to do with this one is we're going to say, all right, well, 3x plus 27, because the thing underneath the radical has to be positive, has to be greater than or equal to 0. And then we can just solve it, right? subtract 27 to both sides. Got 3x is greater than or equal to negative 27. And we're going to divide by 3 to both sides. We're going to get x equals, not equals, is greater than or equal to negative 9. And so when we are writing this, because this is our continuity area, right? We said, where is this working? Where is this going to happen? It's where, so this is our interval that actually works. And it starts at negative 9, and it's equal to negative 9. And it goes all the way up to infinity. So it's going to look like this. It says, describe the set of x values where the function is continuous from negative 9 all the way up to infinity, which is what we found with this square root thing. Okay, let's keep on going. So now here is what we have to do for something like this. Notice we don't have a picture. Notice we're trying to figure out what's going on here. So the first thing you should always do when you've got something like this is try and simplify it. See how the top x squared minus 3x minus 4, you can simplify that top. So we're going to, before we even start, we're going to rewrite this. We're going to factor out the two numbers that multiply to negative 4 and add to negative 3 are x minus 4 and x plus 1. So here's the thing. This is going to operate like this, right? Same thing. All we did was I factored out the top, and look, the x minus 4, they cancel. So when we look at this problem, when you've got something like this, just break this down real quick and rewrite it. Now we know that it's x plus 1 everywhere except 4, because it's not allowed to be 4, right? Because there's a hole there. And when it's not x equals 4, then we can use x plus 1 as our answer. But here, when it's 4, the answer will be 5. If this has a discontinuity anywhere, it's going to be at 4, right? That's the only place that it's going to have a discontinuity, because this is a rational function with a hole at 4. And then it's a break at 4. And so we need to figure out whether or not this 5 sort of follows the program. So the real question is, at 4, does x plus 1 equal 5? Or maybe even better, does the limit as x approaches 4 of f of x equal 5? Because if it does, if the limit's 5, if it's going to 5, and then at 4 we just put a point there at 5, well, then that hole is cleared up and we're good. It's continuous, right? You know, imagine for a second we've got our function here. I don't know, it probably looks something stupid like this, but at 4. Actually, here's how it does look, because it breaks down to x plus 1. So I'm going to draw this properly. But at 4, right, that's too big. At 4, there's a hole. And what we need to do is we need to see, hey, does this piece just sit right in there and fill that hole? Is this the munchkin? Is this the donut hole to our donut? So let's look. If it's true, then these should be the same at 4, right? So what's 4 plus 1? Hey. So this point is going to just sit right there. It'll sit right there. And so it's going to plug up our hole. And now there's no discontinuity anymore. So the function here is continuous from negative infinity to positive infinity. So the check we need to do is, okay, well, there's this piece missing here. Does it match? Does the thing all come to the same place, and is that hole filled in? Okay? So something like this, try and simplify what you can, and then see if this normally would go to that spot. Even though it's been kicked out, is this supposed to go here? If so, then we're all good. Okay. Now here we've got a limit, and we need to know, first of all, continuity. Let's start with continuity. Do we have any of those problems from earlier? It was a cosine, right? It's all cosines. We don't see any divided by zeros, any negative square roots, any natural logs less than or equal to 0, no tangents, no secants, no cosecants, no cotangents. So the thing of it is, we're here, continuity-wise, it's continuous from negative infinity to positive infinity. And it's going to, maybe they ask you, hey, is it continuous at negative 5 pi over 6? It's continuous everywhere, bro. Of course it's continuous here. It's continuous everywhere. So we good. Now let's actually find the limit. Well, since it's continuous, we just plug it in, right? That's the thing. If we've got continuity, if we can identify that our function is continuous everywhere, well, then limits are easy because we just plug it in. Anywhere we see an x, we just plug in negative 5 pi over 6, right? Well, okay, so let's do this. Let's do our order of operations here, because this is kind of complicated looking. Okay. There should be another parentheses. Okay. So let's start from the inside out, right? Well, the 3 and the 6 simplify down, right? So what we really have here is this thing, right? Cosine 3 times, and the same thing here. Let me try to economize our time here. This is the same situation. So we've got the cosine of this minus this. Okay, so cosine of negative 5 pi over 2. Oof. So when you're dealing with this, don't leave it like this. Spin it up. Add 2 pi a couple times until you're between 0 and 2 pi, so it's easier to work with. So negative 5 pi over 2, we're going to spin it up 2 pi to get those same angles here. Well, plus 2 pi, that's plus 4 pi over 2, negative 5 plus 4. So we got negative pi over 2 now. I'm going to do it once more. Go up 2 pi again. We got 3 pi over 2 now. So it doesn't matter. I mean, you can remember that negative 5 pi over 2 is here, but I know we got a time for that. Well, I mean, okay, so what you could do, if you wanted to, you could like start at 0 and then count back 5 pi over 2. So 1, 2, 3, 4, 5. And that would tell you that it's in the same spot as 3 pi over 2, but you can also do it this way. It doesn't matter which way you go. It doesn't matter how you figure out that it's down here. Just figure out that it's down here. And here the cosine is 0, right? The x value here is 0. So this whole thing is 0. And so what we really have is the cosine of negative 5 pi over 2, which is this, right? So that. So 0. And that's the end. So to review with this one, the cosine function is all that we see here anywhere, just cosines. So our continuity is undisturbed. We have full continuity, full range of motion from negative infinity to positive infinity. Nothing in between is kicked out. So now we're just going to plug it in and figure out our answer. So we plug in negative 5 pi over 6. And then we simplify everything down to make life easier for us. And then so we find the cosine of negative 5 pi over 2 is actually the cosine of 3 pi over 2, which is 0. And then so we do it again now because it's the same situation. And then we get 0. Okay. Same idea at this one. Actually, so what's happening here, I'm going to go back so we can talk about, is the same thing what happened here. They're giving you a rational function that has a hole at the spot we want to look at. And so we're going to simplify our function to make the hole not be there anymore. So the first thing, I'm looking at this and I'm saying, okay, so we know that if I plug in 6, it's going to give us a 0 on the bottom. I don't want that. So I'm going to first, to make my life easier, everything has a 6 in there. So I'm going to divide everything by 6, right? So just divide everything by 6. 6 divided by 6, 216 divided by 6, 6 divided by 6, 36 divided by 6. See, now it's a lot easier to work with, right? Ain't nobody got time for all these big numbers. Simplify it down. Well, now look, x squared minus 36, that simplifies into x plus 6 times x minus 6. And hey, we got a factor on top, a factor on bottom. And so what we've done here is we've redefined our function. We simplified it down and got to the thing that we actually need to look at. Because this looks like this, but there's a hole here, right? So when, just like in the last one, if we want to look at this on a graph, what we're seeing is this. We're seeing this function, x plus 6, but all this information that we got rid of, this part, right, tells us that there's a hole right there. But now if we were to use this function, x plus 6, I plug in 6, I don't get no solution, right? I put 6 plus 6 is in fact 12, right? And that's what we're trying to say. Basically, what we're going to do when we are given these directions, define g of 6 for the given function so that it's continuous at x equals 6. So basically redefine the function so the hole is gone, right? And then just plug it in. You know, another way to think about it, if we wanted to think about it like we did in that last problem, what we're really expecting to see is that piecewise function that we saw, right? It's 6x squared minus 216 over 6x minus 36 when x does not equal 6. Every other time we're working with that. But when we are not working with that, we know that at x equals 6, we're defining it as 12. You know, so that it's the same thing. Basically, these are the same problem from a different perspective. We did the same thing, right? We simplified the fraction down. We plugged in the number. And we made sure that these two pieces were the same in that spot so that our definition was continuous. And that's the whole thing. So a lot of these are the same concept, just delivered to you with slightly different words, or perhaps telling you to work from a slightly different perspective, but it's the same thing. Here's another one. Again, slightly different perspective, same idea. We want to know what number A is going to make these two pieces the same at 15. That's what it's really saying, right? It says, for what value of A is the following function continuous at every x? Well, all we need to know is, well, x is 15. So when is A going to make this one match this one, right? That's all they're saying. That's all they're saying. So really what they're telling you is, they're saying, let x equal 15. What is A so that the two branches are the same? So they're giving you instructions on what to do without telling you what to do. They're telling you, hey, x is 15. This is where the break happens, right? X is 15 at the spot that we're worried about, because the rest of this is fine. You know, one part's a polynomial, one part's a parabola. We just want to make sure that they're connected here. So let's figure out what value of A needs to be in order to make that true. So we're going to say x is 15. So 15 squared, that's 225 minus 105. That better be equal to, so that 225 comes from here, right? 15 squared minus 105. And that has to be equal to this part. Well, x is 15, right? 2 times A times 15. So what we really have is, let's simplify this and make it 120 had better be the same as 30A. So this is the place that makes these two the same. So let's find the a that makes it work. And I divide both sides by 30. And I get 4, right? And, you can go back and you can check. You can plug it in and then plug in 4, and you can see that these are going to come out to be the same, right? You'll get 120 here, and then you'll get 120 here, so that at a equals 4, this piecewise function comes together, becomes one thing. And that's all there is. So for one like this, where they ask you to find a value of a, look at the two pieces, figure out where they're supposed to meet. In this case, it's at 15. Set them equal to each other where x is 15. Like plug 15 in for x and then solve for a, and then there's your answer. All right, so here we have a technology problem, because you can't do this in your head. You can't do this on paper without it being really, really ugly. And it says, graph the given function f to see whether it appears to have a continuous extension to x equals 0. Because zero's where the discontinuity has to be, right? So we want to know, does the one piece fill the other? Can I go through and just put a spot there and then fill in the function and make it continuous? So what we're going to do, and again, if you have gotten a chance to download WebAtEmu or download Desmos. Actually, you know what? Let me do Desmos. I think we did WebAtEmu last time. Desmos here. So what I was saying was, okay, so y equals, don't they have like a, let's, oh, I think it just does it automatically if I do a, yeah, it does. Okay. So I had 7 to the x minus 1 over x. 7 to the x minus 1 over x. And look, you can actually dial in on that, which is great. I love the fact that you can just keep dialing in 5 ever until it gets to that place where you're sure to it the same number of decimal places that you need to be. So, so the approximation that they're giving, is roughly 1.9459. That is the y value. I don't know if you can see here like when I'm zoomed in, like the heckinest close that I can possibly be. I actually probably zoom in even further, but doesn't matter. And actually you can see as we get closer and closer, it's starting to freak out a little bit, right? So 1.9459, and then we can we're pretty much done. So have a good one. See you on Thursday. So going back to this, the answer here, the y value, the continuous extension to x equals 0, we're going to do 7 to the x minus 1 over x when x does not equal 0. And it's going to be about 1.9459 when x is 0. Or, yeah, there we go. So, and again, it's going to ask you about this number. It's going to want you to give them that number. Okay? Okay, so let's talk about the intermediate value theorem. And we'll do one problem involving the intermediate value theorem, and then we'll be good to go. So when we are talking about the intermediate value theorem, the intermediate value theorem requires us to have a continuous function. If our function is continuous on the interval that we care about, then we're going to be able to say anything we want. So what the intermediate value theorem tells us, if I have 2 points, let's call them A, B, and C, D. If I know that the line is continuous between these 2 points, then what we can say is that I could visually make myself a little box. Here's the x value of A, here's the x value of C, here's the y value of B, and here's the y value of D. And any point, any y value that I want between B and D has a corresponding x value between A and C. That is to say, if I pick this point, I don't know, let's call it 5. If I pick this out here, there's some x value along this curve. I don't know, we could call it 3. So if I pick a 5 because it's in between B and D here, then there better be an x value to go with it on this function, and vice versa, actually. No, I take that back. Doesn't have to be vice versa, but it does. So if I pick a y value, there has to be an x value to go with it. So, and the reason why this is important, and if we look at this problem right here, let me I'm trying to move this off to the side. I'm going to move you over here. I'm going to squish you down a little bit. So if you know that for basically y between C and D, there's an x value to give it to us. And so that calls into question this thing right here that we're talking about. A continuous function is known to be negative at 8 and positive at 9. Why does the equation f of x equals 0 have at least one solution between 8 and 9? And so, like, again, you go through, I'll Pretend like this is our little calculator window. If you know that it's continuous from 8 to 9, right, for the x value, and let's say it does something like this. No matter how we connect from this point to this point, it has to cross 0. No matter what we do. But Mr. Webster, what do you mean? How is that even possible? Well, look. No matter what I do, no matter how I try to, let's just go, okay, well, here, I did it this way. Let's try and be tricky. Let's try and be tricky. Let's try and not cross this line. Okay, well, I don't want to cross, but I do have to get to that point. Shoot. I have to keep going up. I have to cross that line. So no matter what you do, you have to cross this line to get from here to here, because continuous, right? There's no break, so it has to actually cross this line, right? So that's what they're trying to tell you. And that, you know, I'll share the math version, how it's supposed to look. But basically, if you understand what I'm trying to say here, the mathematical words are going to come just fine. All right, we've got one more problem. And then we're good to be done for today. So once again, this is going to ask us to use a graphing calculator, because ain't nobody trying to graph this by hand. So let's bring back Desmos. We want to figure out whether it does or does not have a solution. So they're telling us about cosine of x equals x. They're trying to have us graph that. And I don't know about you, but like, okay, well, here's a line, so there must be, but like, I don't know how to, your graphing calculator is not going to let you do that. Desmos will, apparently, which is nice. But actually, oh, that's kind of cool. So if we wanted to do this in a graphing calculator, we sort of have to rewrite the function. So we always do y equals. And so what I would do is I would just take the x over to the other side. Cosine x minus x. Actually, look, do you see how these two cross in the same place? At this spot, you know, and I'm going to keep zooming in. Hey, welcome back. Welcome back. Don't worry, I've got the thing recording, so you'll be able to look at it on YouTube. So once again, you look and we get 0.7391 as this spot. But what if we didn't have access to this? Well, what we can do is we can find, basically what you could do is you could find 2 points, one of them's positive, one of them's negative, and then you could show, hey, well, this is it's in between these two. And actually, to be honest, this is what these Texas Instruments calculators actually do. Let me show you what I mean. So the answer is like 0.7391. But here, let me show you how a Texas Instruments calculator does this, because it's slightly different. So when you've got a Texas Instruments calculator, or any type of graphing calculator, to be honest, here's what you're looking at. Let me make sure my window is nice and good. This should be fine. Okay, so just like before, we have to graph a function. We can't do cosine of x equals x. But what we can do is just like what I did in Desmos, y equals cosine of x, close parentheses, minus x. And I'm going to go to the trace function. What you're going to see, hey, it probably goes to 0 right there. Let's change the window and make the minimum x like -2, just so it's easier to see that it does, in fact, cross. But anyway, so you look here and you see how it definitely goes through. And instead of trying to like zoom in, you can use there's some calculation features. The one we care about is the one that says 0, right? We're trying to find the 0. So we see the question is saying, hey, find a left bound. So just, get it close as you can there. Hit enter. Then it's going to ask for a right bound. And look, it's using the intermediate value theorem, right? Between here and here, we've got, it's continuous. And then we're going to sort of get it close so that it can run its little computer algorithm. And then what I said, 0.739, here's 0.8, which rounds up to 1, 0.7391, 0.73908,513.